Thank you for the introduction. I'm Ying-chih Yang. Today I'm going to talk about European Processor Initiative, which is the Europe's plan in the ExaScale. The title will be that EPI Euro Strike Back on HPC, which is on top 100. Then I'm Ying-chih Yang. I represent the EPI Consortium to give this talk. Here now we have lots of keywords about European Union, automotive, HPC, Euro HPC, simulation, supercomputer, others. And this is the scope that in the EPI that we are going to cover, because this is the, when we start this project in European Consortium, that this is the goal that we have been set to ensure that we provide a long-term roadmap in Europe to foster European technology in the future processor. So EPI is a Europe ambition to design a roadmap in the European low-power processor, which is targeting that extreme computing. This is the ExaScale machine in 2023. And also the high-performance big data market. And in the meantime, that we are also going to target emerging applications, such as the HPC in the automotive market. And to answer this, that EPI is an FPA, Framework Partnership Agreement, among 23 members, which is a partner in the project to answer to the code, Horizon 2020 ICT 42, 2017. And the project has been kicked off, started end of last year. So this is a month 2 of the project. Then FPA is a framework partnership in agreement that we usually do that in Europe to ensure that several partners working together on the same topic and for the same goal. Then our mission, EPI mission is very simple. Ensure the European independence in high-performance computing processor technology, which we believe that is a key to ensure Europe long-term industry. The goal is simple, that we want to align to the Euro HPC roadmap in 2023 for ExaScale. Goal is very simple. And tentative that we want to also shoot for providing a Gen 1 processor, we call it REA, to one ExaScale machine by 2021. But all of this that is a goal. In order to achieve this goal, and also not only as a one-time project, we want to ensure that this is built on a solid, sustainable, long-term, kind of a healthy economic model. That means that we need to go beyond traditional HPC market, but also look for other market, because HPC market is a fraction of the market today, that not enough to sustain such complex processor design, manufacture in the long run. We want to address that the main market that is in Europe today, that is the automotive manufacturing market. So our vision is that we want to develop a processor family in Europe made, starting from the high-performance computing market, and then go for connected mobility, shoot for automotive driving, which will be starting from Gen 2 of our roadmap. Will be preparing for a driving automotive, this kind of mobility computing platform beyond 2023. In the meantime, now we want to explore other markets, such as a hyper-server, cloud computing, in the meantime. And what we are doing is we try to leverage the need from those 3 different markets to seek for a technical synergy between this market and try to aggregate the most of the financial support to ensure this activity can be sustainable. So in order to do that, that's the reason we formed an EPI Consortium of 23 different members from different markets. So for EPI Consortium, first we have Bull. Bull is the coordinator of this project. Bull is part of the Atos group starting from 2016. And Bull is one of the oldest technical companies in Europe. more than 80 years, specialized in supercomputing design, manufacture, and also interconnect. And I'm from Bruce, assigned to this project as a lead project for the project, and also in the steering committee of this project that in charge of the general purpose processor design. And that we have following industrial members like E4 Computing in Italy, specialized in high-performance system design. Extros in Germany, specialized in high-speed internet network design. Semi-dynamic in Spain, high-performance processor design. ST Italy, in charge of the power conversion design of this technology in this project. We also have Infineon that providing a secure MCU because Infineon is the #2 in automotive business today, and also #1 in the power electronics today. Carre in France, supporting a real-time processing technology, which is a massive parallelism processor array, which will be used as a real-time performance processing functionality that in our project as a building blocks. Again, we also have the automotive counterpart like BMW and Elektrobit in Germany that they are specialized in building automotive systems, and which in this project that they are supposed to build out the HPC demo system in the first phase of the project, because the first phase of the project lasts for 3 years. On the counterpart, on the economy side, that we have the BSC, who is a user and also the technology provider in this project. BSC is the world famous supercomputing center. And in this project, they are going to design a spatial accelerator that's supporting long vector. CE, the same in France, that user of a supercomputing center, and also that is also supplying technology and also design in this project. Synerca, Fraunhofer, Force in Greece, GNC in France, Zurich in Germany, Substar in Netherlands. They are the world-class research center in this project that joined work to provide not only a code design at the processor level, because most of the time that when we have ExaScale program that they provide a design in the system level. But this time they start from the processor level to provide different level of integration. Then beyond that, we have Chalmers from Sweden, ETH Zurich from Switzerland, University of, and also that IST from Portugal, Unibor, and University of Pisa, which in charge of different part of the project to provide an ecosystem. That's the 23 members. Then after 23 members, we have more members to ready to join the project. So for all the 23 members that they are from the research to industry, that they are forming the kind of a group and consortium to provide a key European technology as a foundation of this project. After that, because this foundation of a European project is not sufficient to make a processor chip that is powerful enough to compete in today's world in ExaScale. So we work with the ecosystem around EPI, that's with ARM, Linaro, and also EDA tools to ensure that we can provide a solid solution for EuroHPC, the ExaScale plan. Then in order to merge those efforts, try to make it into one project, one product, then in this case that we need to have one single entity that is responsible for the tape-out, for the manufacturing, for finally promotion this system in the market. Then we need to have one single entity. Now today we call it EST, European Silicon Technology. This company formed would be in charge of this activity. And after that, after the product has been produced, then this will be EPI project in front European scope that you will support a proof of concept, starting from building the EPI common platform, PCI Express card, to the EPI motherboard, and also to EPI HPC blade, which would be used in the pre-ExaScale system for demonstration. And at the end of the project, that for the phase 1, we'll have a EPI ADAS demo system built by BMW. And in the meantime, since EST is an entity that will also provide this chip as a product to other system vendors. So that's the plan that we want to build. In order to reach this plan, that what we want to develop is a common platform. So for this EPI common platform, that's been from today that we start the project, and we start to develop key technology in this common platform. We want to make sure this common platform can be extendable to next 5 or 10 years. So which in this case that in the beginning of the project that we will not have a lot of IP and functionality blocks in this project, in the Gen 1 product, we call RARE. So for Gen 1 product, we rely a lot on external IP, which is fair. And we use Gen 1 product that we use on processor core, high-performance processor core that in this project is a main computing power to the chip. And this chip would be also equipped at a RISC-V-based oscillator proof of concept to ensure this heterogeneous processing platform in the Gen 1 that can be worked in the pre-ExaScale systems, and also as an automotive proof of concept at the 2021. Then after that, this platform would be delivered as a pan-European research platform for HPC and AI, and also as an EPI IP-led non-transferable. Then after the Gen 1 product that we start to collect more and more IP after the 2 years, then this will be derived into Gen 2 product, which will be in another phase of the EPI project from European. In this case, that this will be shooting for ExaScale, because a lot of time that all the acceleration blocks in the Gen 1 product will be mature enough, have enough software support, system support. The programming model will be correct. So we'll be able to extend that to ExaScales. And also that this same chip will take into kind of automotive certification to ensure that in 5 years, before 2025, this chip, Gen 2 chip, will be ready for automotive market at that point. And finally, that's too far away from now, but that's the future that in Gen 3 that we'll be able to provide something. So for this common platform, this basic concept, we want to ensure that in the execution of this project that we want to have the ARM as a general purpose processor. We work closely with ARM to utilize ARM's IP, processor core IP. We try to make that, try to reuse the ISP the best way. Then a majority part of the project from EPI is also invest to design a RISC-V-based oscillator. This would be a RISC-V instruction set plus the vector extension to ensure that we have a good support for long vector in scientific application. And in the meantime, that we'll have RISC-V to be used as a root of trust and also power manager. At the same platform, that we also include 2 other components. The first one is from CloudRay, which is real-time, that's just like I said, is a real-time, kind of real-time target processor, which is specialized for FP32. And you'll be able to provide a requirement that meet automotive market. And also there will be another block that is called Mentor, embedded FPGA. This will provide a reconfigurability in our chip to ensure that this chip is flexible enough, not only in the given application target, but also provide some reconfigurability in the future. So this will be provided the HPC pre-ExaScale system, and also of the automotive CPU prototype, and also in the meantime that for a research program. Because for a research institute that they will be able to use not only the software part, but also for the FPGA part to design the component that is close coupled to other processors system on the chip. and also to couple to high bandwidth memory that we provide in the system. So to go more detail about EPI common platform in the Gen 1, this is what we are going to provide for scalability. Scalability-wise, that from the bottom part, we have a functional block level kind of a scalability. We want to provide a heterogeneous platform that will integrate lots of the unprocessed code, plus some the EPIC and also MPPA and also FPGA blocks in the design, so that this, in the generation 1 of the chipset, that we've been able to mature a heterogeneous computing platform. Then on the chip level, that we are exploring and doing some integration. First with HBM. Second is with other different chiplets, because in the meantime that we want to aggregate more than one dice on the chip to ensure that we have bigger enough sequence service on the chip. And also that we are providing the inter-chip scalability. So the main goal of this common platform is to ensure that this same platform would be able to scale from different market needs, from HPC to automotive for eHPC, but also scale from the need from today to 2025 and beyond. Because from our view of ExaScale processors, it's an ExaScale processor that you need to have a specialization. So that means that without specialization, like ARM with SVE, or maybe like EPIC that specializes in vector processing, it's not possible to meet the energy requirement. And the second point that it's an ExaScale processor, we believe that you need to have enough byteflow, because this is the key index that we need to sustain, ensure that the general application can be ported onto a processor easily. So the two index, specialization and also byteflow. So to implement that, the way we do is that first is that we have such common platform to be able to integrate those heterogeneous computing units between ARM, between oscillator for long vector, between the oscillator for a real-time application, including FPGA. Then to ease this heterogeneous integration, that we are using 2D mesh to ensure we get scalability in the die size, in the computing power of a chip. Then that we integrate memory closely. And this platform, that what we are shooting for is around 0.5 to 1 byteflow. And then adapt the next chip and die-to-die bandwidth to ensure that we have efficiency share and exchange between different chips in our system. So just now is kind of our view of an ExaScale processor. And this will be our kind of implementation of our view. The RAIA is the generation 1 of a processor that in the pre-ExaScale system, that we are going to have 2 processors that work in the node, providing DDR and HBNSS. In the second generation of a chip, that will extend up by 2 by 3 times of a computing power by the support of oscillation logic inside that by a better ARM processor providing longer SVE engine, that we will be able to kind of form a bigger system in one node. Then potentially that if there are need of multiple chips that we want to aggregate them together by a high-speed link hub in between that. So that's our view and our implementation in EPI towards ExaScale and potentially post-ExaScale. So generation 1 RAIA, general purpose 1 including DRAM support. Generation 2, specialized for computing. Generation maybe 2.5 to link it together efficiently. So implement that in the EPI phase 1 of the project, that we have 5 streams in the project. The stream 1 is a common stream that providing co-design architectural efforts. Stream 2 is a general purpose processor, which is the one I led. And stream 3 is acceleration logic. Stream 4 is for automotive requirement. Stream 5 is administrations. Then they are in charge of different part of the project. Stream 1 that mainly for co-design architecture, system software design, and key technology for a common platform. And also stream 2 for other things, for implementation of a chipset and also proof of concept. Stream 3 is try to ensure that we have enough acceleration plan for the future. Stream 4, automotive requirement. So one thing that guides us all in the project is that since this is the implementation of European technology, that we want to ensure that we have enough co-design between the user of the application and also the designer and architect. So the way we partition is that we are working with application expert organized by juries in the consortium. Then they serve the requirement that from architect from different streams, since we have 3 different streams that implement 3 different requirements. From the chip side, GP1, from the acceleration part for building blocks, and also from automotive. Then they provide different requirements in the chip level to an application expert. In the meantime, they put the spec that to the model, and which the model that will inherit the model we are using from Montblanc projects. And this model will be prepared by CEA and also BSC in the group to make sure that architecture, their idea and their planning was correctly implemented by the model in the early stage of the project. And then application expert that they can answer to a requirement for architect to provide a benchmark result to support what kind of benchmark is required in this kind of a core design platform to ensure that the processor we have designed, the building block we have designed is meeting the requirement to meet the goal. So for the model itself, that first we have the 4 different models here. The first one is a high-level model, MUSA, provided by BSC. It's inherited from Montblanc projects. Will be able to provide high-level simulation input, logging of the trace, so that we can replay to verify that the chip performance in the interconnect level, in the memory hierarchy level. A second level that we work with Gen 5 model to kind of work as a verification model. This one would be used to verify the main design model we are maintaining from on with the face model and cycle model. From our internal design that we are using System C to integrate model at different level, QMove level, and also others together. So the complete scheme will be like this, a little bit complex. But overall, the idea is that we are matching the requirement of a different level or the models to ensure that the architecture is verified early stage in the project. Because what we provide is a computing platform. Then this computing platform will be able to be configured at later in time before the tape out of the project about a requirement. So that's all about hardware. Now we talk about a little bit about software. So for EPI, inside EPI project, that there's another part of effort being invest into the software. So EPI, from EPI and EST point of view, that we will supply the full software stack for the processor. But since this is a processor project, this is not a Euro HPC project. So we are not building a system level. We will provide a system level reference design, but not a complete system stack design. So this would mean that we will provide a reference firmware UEFI to end-user tools, compiler library runtime by leveraging from our ecosystem, and to enable the direct use of the processor design. And the tools will be developed with a partnership with our project manager, such as Atos, BSC. In the meantime, that will also be provided by the ecosystem partner from ARM and Inaro. And the other scientific code that will be used as a basis to do the code design. Then this would be ensure that our design set, hardware-wise, is match our design need from our application. Then our industry partner like BUOS, like EVO, will be able to design a full software system environment for each HPC and eHPC. So for EPI software infrastructure, or maybe we should not call it software infrastructure, it's a system infrastructure. Starting from the bottom, now we have EPI processor built by BUOS, Venover, CEA, Carre, Mentor, BSC, that several building blocks, plus EPI response hardware built by BUOS and EVO computing. And plus the low-level software power management provided by Unibo and also provided by Pull&Run for security. And the operating system part, BSC, BUOS, and FORCE will be in charge of building the operating system of the platform. But in the meantime, that majority of the effort will be leveraging from ecosystem partners. Then from the code design part, Juris will lead this part of the activity by providing code design exploration space between several selected tools. Then here is an example about how many tools how many applications we have selected. AB Init, CB2K, ECRs, lots of them. Then in the meantime, that the BMW group will be working with Electrobit plus the microcontroller from MCU, from Infineon, that build an automotive embedded HPC system support. Then for the programming tool and library that we will leverage from the previous Edmond Brown projects, plus in this project that we allocate resources to build not only the operating system, but also the tools, including the libraries. But most of the part we are leveraging on the ecosystem partners. And in the end, that BUOS is industry partner in the project that will be in charge of integrate them into one reference platform. But since that EPI and EST is the kind of try to provide a processor not only to BUOS, but also to other system vendors. So this will be only used as a reference platform. So with EPI, that Europe have an ambition to repeat the Airbus success. In 1970, we have started Airbus project to start to integrate the aerospace effort, aggregate them together in Europe. Then they have been successful, and they are successful. So this is what we want to duplicate in 21st century, that to do the same thing again, to aggregate all the effort in the European processor design together by EST to become a successful story in Europe. So that's all I have that to be the same thing is that lots of things that is covered. Then EPI want to cover those topics. Then the target for us is try to make European HPC European again. This is our vision, our goal, and our mission. So any question?
No, thank you.